unit. If you can find it before the end of the talk. I think this minus needs to be a plus. Gauss sometimes. Anyway, thanks very much for the introduction, and thanks very much for having me. I have to say I've been having a lot of fun at this conference. In fact, so much so that you might have noticed the title has changed after some discussions I had yesterday, and it was so much fun that I thought I'd adjust the talk a little bit to stay a little bit in the theme of some of these discussions that had been going on. So my main purpose today is to tell you a little bit via a sort of really roundabout way about the conjectures that Darmon and I made a couple of years ago, the relations perhaps with other RM invariants we've seen, as well as a work in progress on the proof of some of these conjectures that we stated back then. And so I'd like to begin with a setup that's kind of familiar from yesterday's talk of Elias. And so I should say I have exactly 10 slides. I know it says 14, but there's 4 title slides in there as well. So I did this on purpose, so I don't have to click too often, so the information doesn't appear too much. If ever I should still click too fast, feel free to stop me and make me go back. So this first slide, you already sort of know this story. I just want to briefly remind everyone of how it goes. And so the story starts with Gauss. And Gauss was very interested in the disquisitiones in discussing quadratic forms, as many people have been before him. And what Gauss did is he studied quadratic forms, binary quadratic forms, so with integer coefficients, which I'll denote here by a, b, c. And one of his main innovations was to consider not an action of the group GL2Z, but rather SL2Z, slightly different than what people had done before him. And this was a key insight because the action of SL2Z on quadratic forms is given by what we nowadays call the usual thing. And this action preserves the set of quadratic forms, it respects primitivity, and it also preserves the invariant, which is the discriminant of a quadratic form a, b, c. Okay. So this action of SL2Z has the pleasant feature that if you take the set of primitive forms of a fixed discriminant and you quotient out by this action of SL2Z, where if in case of negative discriminants, I'll insist that I only take positive definite forms, then actually the set of equivalence classes for the group SL2Z has a group structure. So there's more structure than if you would have gotten from GL2Z, and that was his main insight. Now, Gauss did think about it in the language of quadratic forms. Nowadays, of course, we prefer to think about it in terms of Picard group or class groups of quadratic orders. And so there is a bijection between the set of SL2Z equivalence classes of quadratic forms and the narrow class group of the quadratic order O of discriminant D. It's given very explicitly by this bijection. So it endows the quotient with a group structure, and Gauss furthermore developed what's called reduction theory. So he identified very specific distinguished elements in every SL2Z orbit, which he furthermore could enumerate very, very efficiently. And so he did a large-scale computational study in the disquisitiones with thousands of examples. And this is what he noticed, as we learned also yesterday in Elias's talk. So it's not exactly what's in the disquisitiones, but in the modern language, this is what he would have conjectured if he had been working in the same setup. So for negative discriminants, he observed that it's very rare to have class number 1. That's precisely for these 13 discriminants that this happens. Whereas for positive discriminants, he's very careful to say this, but one can read in what he writes that he might conjecture that this happens infinitely many of. Of course, nowadays, Cohen-Lenstra heuristics make this much more precise, and for prime discriminants, for example, this should happen about 75% of the time. So very, very often. And so there seems to be a very different story going on depending on the sign of the discriminant. And that's a little bit the theme that I want to take for my talk today, sort of putting into contrast some of the differences and contrasts between the two setups. And so I would like to start with the classical setup of CM theory. And I'll focus specifically on the 2 types of invariants that play an important role historically, namely the elliptic units and the singular moduli. We'll discuss a little bit the proof of Heegner and some geometric techniques related to the method of Chavorty. Then I'll go to the setup of RM theory and discuss a little bit in parallel, hopefully, what I said in the classical setup. So that's the game plan. All right, so back to the CM case, the classical case. So the class number 1 problem was resolved by Heegner, as we also learned yesterday. But the proof of Heegner was quite different from what we saw in Elias's talk. And so his method really it relies on modular functions, but it relies really on the relations between the two types of CM invariants that we just saw. And I'll be a little bit more specific. So the two modular functions that you find in Heegner's work, I put them side by side here. The first one is the cube root of the J function, which he likes to call gamma 2. And the cube root of the J function is a modular function which has the wonderful property that if you evaluate it at a quadratic imaginary argument tau, where the discriminant of this tau is not divisible by 3, so there's one condition that we'll explain a little bit later, then actually the outcome is an algebraic integer, and that algebraic integer is of degree h of d. So h was my notation for the class number. Okay, so that's the first type of function that shows up in his work. The other one is CM values also of these other modular functions. He looks specifically at the Weber functions, which have the following very explicit infinite product representation. Now, if you look at these two sets of CM values that you get, for instance, for the same CM point, they have drastically different arithmetic properties. So the singular moduli, the invariants on the left, are algebraic integers, whereas the elliptic units, they're always 2 units. And so here's an example. So for instance, if I take the J invariant, which is a cube of gamma 2, of this CM discriminant of class number 1, we should get an integer. And this is what this integer is. It's highly factorizable by lots of crazy-looking primes, whereas the Weber functions are much more rigidly structured, part of an Euler system, so they obey much more stringent rules, and as a result, their arithmetic is more structured in that you always get 2 units. Yeah. So yeah, here I took the norm, but anyway, I'll get back to that later.
F squared, really?
F squared.
F sub 2? Okay, it's F squared.
F squared, yeah. So it's the usual F squared. That's the one that shows up in Heegner's proof. So the F squared is not an integer. So it's not in the base field, but almost. So I'm cheating a little bit with this norm here. I'll get back to that in a second. Okay, so these two sets of invariants play a crucial role, but each by themselves, they don't actually tell Heegner a lot. What tells Heegner everything he needs to know is the relations that exist between them. So in fact, these functions are related by some polynomial relation. And from that polynomial relation, he constructs out of some putative class number 1 discriminant an integer solution to the following equation. So the equation is a cubic equation, which is cooked up. So the x and the y are some expressions in the f's and the j, which I won't recall here. And they satisfy this cubic relation. And Heegner's argument hinges on the fact that the solutions that you get by evaluating these functions will give rise to integer solutions of this cubic equation. Whereas this is an elliptic curve, and so you can use your favorite method to find all the integral points on this elliptic curve. That's what Heegner did, and he concluded that all of the integral points that he found were accounted for by known discriminants of class number 1, and therefore there's no other ones. That was sort of his idea. Okay, so a lot later, Sayre gave a beautiful interpretation of this argument, which might feel maybe a little bit ad hoc. Where does this relation come from? And Sayre observed that actually this equation that's standing here is an equation for the modular curve, non-split Cartan modular curve of level 24, where the plus denotes that I'm looking at the normalizer of the non-split Cartan subgroup. So he made this very nice observation. And in fact, this observation gives you also a strategy to give new proofs of class number 1. And so let me tell you first what the non-split Cartan modular curve is and how this leads to a proof of class number 1 in general. So it's a composite level, but I'll work with prime levels henceforth because it's maybe a little bit cleaner. And so I'll tell you that whenever we have a prime P, we can look at the points on this non-split Cartan modular curve, and they actually classify elliptic curves so that when I look at the image of Galois in, well, acting on the P torsion of this elliptic curve, then that gives me a subgroup of GL2 FP. And there's a very specific subgroup of GL2 FP that I'll be interested in for this modular curve, and it's the normalizer of a non-split Cartan subgroup. So if I look at FP squared without the star, that's a degree 2 or a dimension 2 vector space over FP, not canonically so, but it is. And so what you could do is you can let FP squared star act on FP squared just by multiplication and view that as an action on a 2-dimensional vector space, and that gives you some embedding into GL2 FP. Requires you to choose a basis, but if you choose a different basis, you get a conjugate subgroup. That subgroup is almost maximal. It's contained in its normalizer with index 2, and the normalizer is a maximal subgroup, GL2F. So that's what the non-split Cartan modular curves. And now you can imagine what the composite definition will be that gives you that observation. Now, Serre, by this observation, really conceptualizes this proof of Heegner very, very nicely, because you see, whenever you have a CM elliptic curve E, defined over some number field K, you get an associated K rational point on this non-split Cartan modular curve. Not always, there's a condition. So you get that precisely when P is inert in the ring of endomorphisms of this elliptic curve. But this happens for a fixed elliptic curve with CM half of the time, for half of the prime. Now, this point is not just a rational point, it's actually an integral point, because it's a CM elliptic curve, so it has potentially good reduction everywhere. It's never allowed to reduce to any of the cusps. So integral is meant here with respect to the cusps. It's a stronger version of integrality than what we just saw in Heegner's proof. Okay. The nice thing is that, and this is the underlying observation of all of Heegner's proof, really, is that whenever you have a class number 1 discriminant, this condition of being inert is automatically guaranteed whenever the discriminant is large enough in absolute value. So here's a silly bound, but whenever the discriminant is large enough and not divisible by P is going to be automatically inert. And that's because P has to be represented by some quadratic form like x squared plus delta y squared. And that can't be if delta is too large. It's a very silly kind of reason. It's a nice observation, but it really underpins the whole proof. So that means that if you have some finite list of class number 1 discriminants and you suspect it's the full one, you just have to rule out that there's no discriminants larger than that still have class number 1. And that you can do by saying, well, by this observation, there would have to be some other integral point on this non-split Cartan modular curve, but we didn't find it, so it doesn't exist. That's sort of the idea. Okay. So this naturally motivates an interest in finding finding integral points on non-split Cartan modular. Of course, there's a question that's, and this is already a difficult question, but there's a question that's even more difficult, much more difficult. And that's to find, in fact, all the rational points. And this question is also very important because you see, Serre proved that whenever you have an elliptic curve, and you look at this representation of the Galois group on the P tangent of that elliptic curve, then that's always a surjection as long as the prime P is large enough. So we proved that the notion of large enough, it's given by some constant which depends on the elliptic curve. And he asked the question, is that really necessary, this dependence on the elliptic curve? In other words, if P is large enough, will this image always be surjective for any elliptic curve defined over Q? That's the Serre uniformity question. It's a question. Specifically, the conjecture is that 37 is always enough. 37 is because there exists an elliptic curve over Q that doesn't have CM. Sorry, I didn't say that. This elliptic curve needs to not have CM. That's very important. So for a non-CM elliptic curve, it can actually happen that 37 is necessary because there is an elliptic curve over Q with a rational isogeny to another one of degree 37. Okay, so can we always take 37? Well, to tackle this question, all we have to do is find all the rational points on all the non-split Cartan modular. We've reduced the problem to a seemingly completely intractable problem, but the nice observation is that you can now say, well, you see, if it's not a surjection, then the image is contained in some maximal subgroup. So if we have a classification of all the maximal subgroups, we can just go through them one by one and try and tackle them one by one. And we do have a classification of all the maximal subgroups. The maximal subgroups fall into various cases, all of which have been settled, except the non-split Cartan family that I just discussed for you. So Serre discussed the exceptional cases. So sometimes it's possible that projectively you get an exceptional group as the image, but those he could rule out quite easily by showing they don't even have any QP rational, let alone Q rational. Mazur did the bulk of the work by settling the Borel case. So you can never have an image that's upper triangularizable whenever P is larger than 37 is what he proved. In other words, there's no rational isogeny of a degree larger than 37 for other P. The screen here went blank, but this one is fine. So I hope we're good. Okay, so Bilou, Perrin, Reboledo did another case. They did the split Cartan case. And essentially there also the split Jacobian, it's isogenous to the one of the non-split cartan plus the Jacobian of X node of P. And so they use the X node of P quotient, also constructed by Maser. So they use Maser also in a very essential way, but they beautifully also settle completely the case of split cartan. So that leaves the big mystery of the non-split cartan family completely, of which Heegner, of course, did sort of one case, except it was a composite level, so it's not going to appear in my discussion henceforth. But historically, that was really the first class of curves that was considered at this point. Okay, so what do we know? But the answer is essentially almost nothing. We know essentially almost nothing about the set of rational points on these non-split cartan modular curves outside of small examples. And so here's a table that summarizes, to the best of my knowledge, our knowledge, so as a community. So what I've done here is I've taken the prime P to be just a couple of small ones. I put also the number of cusps here, which is relevant for the integrality discussion that I had earlier. So the set of integral points will be finite from this point onward, because here you have a P1 minus 3 points, etc. The genus I've also put, so here we get the non-split cartan curve as genus 0, 0, 0, 0. 1 is the first time, which happens for 11. So X non-split 11 plus is genus 1. And then here's the dash to indicate here it's higher genus. And it's much higher genus. It grows quadratically. And then the last row is, I put a tick mark whenever we know all the rational. So that's essentially the state of our knowledge. And so there's many people involved with this, and so it goes back. I mean, of course, there's Heegner, who doesn't appear in this table because of his level was composite, but also Siegel looked at X non-split 5, for instance. Ligoza did X non-split 11. Kenku worked out this one, and he worked out the integral points in a very beautiful way. And it's a very interesting case because it's P1 minus 3 points. So you're solving the S-unit equation, which you could do explicitly to show, actually, to give a new proof, and in my opinion, maybe one of the nicest proofs of class number 1. Boran was also involved, Mercury and Schoof, and then finally, with my co-authors, Balakrishnan, Dogra, Müller, and Teitman, we settled first in 2019 the first higher genus case, so it's a genus 3 case, and then a little bit later, more recently, we did also the 17 case. And 19, I don't know if anyone's done it, but it should be perfectly doable by the same kinds of methods. It's just, it becomes computationally kind of rough, so this is where we stopped.
So what is the answer? Like, so
the answer is that for all of the, well, let's say these, the only rational points are accounted for by CM points. Yeah. And so in fact, we expect that this will already keep happening here. So the 37 is only for the Borel case. You can rule out the non-split cartan exceptional images from 13 onwards. That's the expectation. So you'll only find CM point. So in some sense, no surprises are expected. We already know all of those points. We just have to prove that there's no other ones. And every time you do one case, you give a new proof of class number 1. That's kind of, at some point we have enough proofs of class number 1. But still, it's kind of. Okay, so I want to tell you a little bit about this method because it's strikingly similar to something I will talk about in the RM setup, in that it involves the notion of p-adic heights. And so I want to tell you a little bit about how that works, and superficially also about how it reinforces the motto that the p-adic heights are a very convenient way to eliminate all of the complicated geometry that's hiding behind the scenes. In the case of the CM setup, as I'll show you in a second, this geometry is known and very beautiful, but very complicated. In the RM setup, this geometry is not known, so there's a need for such a thing like a p-adic height to circumvent this lack of geometry. So it's geometry avoidance in favor of p-adic heights is sort of the guiding theme. Okay, so how does this method work? And I decided to also say a little bit more about it because it resonates very well with what Elias was talking about yesterday. And in fact, I think the method there was very, very close to what you would see in a Chaboty method. So that's what I kind of wanted to discuss now. So the method of Chaboty, it's a very general method. So it doesn't care that you're working with modular curves. It just says, take any nice curve, so smooth projective and geometrically irreducible, let's say, of genus G, and R will always denote the rank of the Jacobian. And so there's this big condition in the title there, which I like to stress again. The rank is less than the genus, is what I'll assume from now. So it's a geometric assumption we have to make on our curve. And then Chaboty has a very nice proof of the finiteness of rational points, of Faltings' theorem, under this assumption, and that proof can be made effective. And so the basic setup is you take your curve and you embed it into its Jacobian via the Abel-Jacobi map, which you get by choosing a rational base point B. Now, choose a prime of good reduction. That's always a step in a Chaboty type method, which, other than a good reduction, it doesn't really matter which one you pick. Maybe you want to pick it small for some reason, but it doesn't really matter all that much. What you could do is you consider a diagram of the following sort, where you take the global points on the curve and embed them in the p-adic points, and you do the same with the Jacobian, and the maps going across are the Abel-Jacobi maps. And this is a p-adic Lie group, so we can go to the tangent space, which is the dual of the space of differentials, via the logarithm map, and we get a diagram of this form. Okay, and so the insight of Chaboty was, so he proves two things. If you look inside of this space, which is a g-dimensional QP vector space, and you look at the image of the global points on the Jacobian, under the assumption that the rank is less than the genus, this is genus g-dimensional, and this should feel more like genus R, or dimension R subspace, it's going to be a proper subspace. That's kind of the idea. So the closure is contained in a proper subspace, is the first thing that Chaboty shows. And the second thing he shows is that if you take this proper subspace and you intersect it with the image of the curve, you get this proper subspace, the curve will sort of intersect it transversely. It's not going to lie in it by accident or something. So the intersection is going to be finite. Those are the two things that Chaboty proves in this setup. And the proof is very nice, and it tells you that if this condition is satisfied, then indeed there's finitely many rational. The method is also not sensitive to Q. You can put any number field instead of Q, and it goes through without any change. Okay. Now, it proves finiteness, but it's not so clear how to work with these objects in practice. And so it was noted by Coleman that, in fact, you can turn this into an effective method by saying, well, if you contain a proper subspace, you can always find a differential that annihilates this proper subspace of the dual. You can take some form, omega, that's dual to the entire closure of the global points in the Jacobian. And if you do that, then you can consider the following function, which is a function on the p-adic points of the curve to QP. That's obtained by integration, it's a Coleman integral, from the base point B to the endpoint Z of this differential omega. And now you know that as soon as you are a rational point, you factor through the bottom, so you go to 0. But in general, you're not a zero function. You're a locally analytic function that's non-trivial, and that follows essentially from the arguments that are there on the right of Chaboty. So you get a locally analytic function, and its zero set, which is finite, it's a finite set, contains the set of rational points. So if you were able to compute this, you could maybe determine the set of rational points in a very similar fashion than what we saw yesterday in Helias's talks. Find some function, you find the zeros, and then you account for all of the zeros, either by global points or by ruling them out in some other. So luckily, these things are all effectively computable. So this started with the beautiful work of Kiran Kedlaya for hyperelliptic curves, which was then extended to general classes of curves by Balakrishnan and Teitman. This function, this Coleman integral, you can actually compute. You can actually go to a computer, input an equation for this curve, and get out your local as a collection of power series on each residue disk. That's kind of the idea. Okay. So great. So we have a method. Everything is effectively computable. Let's apply it to a non-split Cartan modular. Alas, this method completely fails for non-split Cartan modular curves. This condition, R less than G, is essentially never satisfied. It's never satisfied. Absolutely never. So for instance, for the first difficult case, this case was this a so-called cursed modular curve. Maybe because I decided to talk about this, all the organizers got sick or something. I don't know, this is like the cursed one or something. In any case, that's this curve, and it's cursed, for instance, in this way, because the rank of its Jacobian also happens to be 3. In fact, the sign of the functional equation is so that every simple piece of the Jacobian needs to have an odd multiple of its dimension as its rank. That's just the sign of the functional equation. So in this case, the rank is 3 and the genus is 3. So the method, this kind of breaks down. And so we learn that the first thing you would try and do is you take your genus 3 curve and you embed it into its Jacobian. So, you can wonder how do you do that? Luckily, there's a very nice sort of instructional illustration online that some of you might know of how to embed the genus 3 curve into its Jacobian. It's a very famous drawing. I did not make this drawing. I'm sure many of you know it. It's an illustration of Dan Abramovich embedding a genus 3 curve into its Jacobian. Unfortunately for Dan Abramovich and for us, this will not cut it. And so what we have to do is we see that embedding things inside of the Jacobian is kind of too small. That's the issue. Jacobian is G-dimensional, and the rank of it kind of fills up the whole thing. So we don't have enough space inside of the Jacobian to determine the rational points. And so the fantastic insight that Min-Young Kim had is that you can in fact generalize this whole diagram to a wildly sort of more sophisticated setup that allows you to give more space, in a sense, to the curve by working not inside of its Jacobian, but inside of sort of deeper quotients of the fundamental. And so what I'll do is I'll discuss the sort of the smallest case of this in an anachronistic way by giving you the geometric interpretation first, which came really in reality last. So Min-Young's original framework was already entirely in terms of Galois representations. And then later people put the geometry back in, and that's kind of the viewpoint that I want to take for today's purposes, because it's a little bit more complex. So we want to mirror exactly what happened on this slide, but with an object that's bigger than the Jacobian. So let's see how that goes. So we need to enlarge our Jacobian. There's many ways naively to do that, but the specific way that works very well for these Diophantine purposes is the following. So we still have an able Jacobi map to our curve. I don't know why I have a maps to instead of a normal arrow, but please forgive me. Here's a diagram. And this diagram is essentially the defining diagram for the Néron-Severi group of the Jacobian or the curve, which works really in full generality. So we look at the Picard group of the Jacobian, which I've called J here, and everything that's algebraically equivalent to the trivial line bundle is the pic 0, and the quotient, by definition, is the Néron-Severi group, which is a finitely generated group. So it's a finitely generated set function. We can do the same thing for the curve, and the maps going down are just restriction of line bundle to the curve embedded inside of the Jacobian through this Abel Jacobi map. For the pic 0, we get an isomorphism. That's just an identity map. But of course, the pic J could be much larger than the pic X. And the Néron-Severi group of the curve, that's just given, this map is just given by the degree of a line bundle on the curve. That's always an integer. So we get a commutative diagram like so. Now, suppose we're lucky, and suppose we're working with a curve that has a lot of endomorphisms in its Jacobian, like modular curves. So there's a lot of extra symmetry to play with that gives us a lot of extra elements of this Néron-Severi group. And so suppose that we could choose an element of this Néron-Severi group that is not 0, but that maps to 0 when you restrict it to the curve. Okay, let's do that. So I'm going to take the diagram of before, I'm going to replace it by these fancier objects, which I now have to define for you. Okay, so in this diagram, so you take a Z. This Z looks a lot like this Z. That's unfortunate. This is not a bold-faced Z. It's an element in there, in the Néron-Severi group of J. So think of an endomorphism of the Jacobian. You're going to pick some Hecke operator. You're going to pick it very nicely so that it is non-zero, but it maps to 0 in the Néron-Severi group of X. It'll come from a line bundle that if you restrict it to the curve X, it's actually going to land inside of this kernel in the pic 0. So now I can change it by an element of pic 0 of J so that it's actually trivial on the curve. So I'm going to take a line bundle that is non-trivial in this Néron-Severi group of J, but that if I restrict it to the curve, I get the trivial line bundle. I'll just get the structure sheet. So that's what I'll call LZ. It's a line bundle on the Jacobian. So the Jacobian has become one dimension bigger. Okay. All right, so the triviality on X is very important because, of course, we need to lift our Abel Jacobi map to an Abel Jacobi map on this bigger geometric object. And that'll happen by trivializing this line bundle over X. So this gives me a map inside. And that's precisely what we'll do. So we'll get a lift of the Abel Jacobi map from X to the associated GM torsor, so the principal bundle associated to this line bundle, which just consists of all the isomorphisms between O and LZ. And this map, of course, a priori, it's unique up to Q star. But Erikshoven and Lido, who this picture is due to, they explain that you can spread out the geometry over Z and make this section unique up to the units not in Q, but in Z. And the units in Z, that's quite a small group, so it's essentially a unique lift now. So we've replaced this object by a much fancier object, LZ star, and we have a diagram like so. So the tangent space here will be also some log P map, and it will now go to a space, a p-adic space, that is one dimension bigger than the tangent space of the Jacobian. So it's G plus 1. And this plus 1 is very, very interesting because we'll put ourselves in a situation where the rank is equal to the genus, like for the non-split Cartan curve that we discovered before. and try and get enough space. And one dimension bigger will suffice in this case. Okay, so what's nice about this GM Torsor LZ star is that we understand completely all of its étale coverings. They were completely classified by Edixhoven and Bertrand. And in fact, if you look at the p-power étale coverings of this thing, you will find that if you look at the fiber over the identity, you get a Galois representation, which is an extension of the Tate module of the Jacobian by QP1. And this QP1 comes from the GM in the fiber. Yeah? But it's an interesting, non-trivial extension. Okay. So if you do that, you can now do a descent argument, just like you would with the Jacobian, by considering p-power multiplication maps on the Jacobian, and then looking at the fibers over a rational point. It gives you a torsor for the Galois representation that you get in the Tate module, so a class in H1F GQ VPJ. That would be a normal descent. But here we're going to enhance this by working instead with this bigger non-abelian group U. And this map log P turns out, and this is the key fact, to factor completely through this association. So what we're going to do is we're going to look in these étale coverings. A rational point in Q will be mapped to the torsor of U that I get as a Galois representation by looking at the fiber of all of these étale coverings over that point, just like you would in a normal descent. Yeah? So you get an association that associates a Galois representation to any rational point. And in fact, this Galois representation knows everything about the image of this, so it factors through this. And that's already a crucial observation, and this is really where the framework of Mignon-Kim happens. You bypass the geometric thing, and you encode everything inside of a path torsor. So just a Galois representation. So the idea is now we've replaced this curve by its associated family of Galois representations, which you can now also view as a sort of a mixed extension. So EBX, B is the base point that I chose, X is a variable endpoint. That's going to be some Galois representation of dimension, I guess, 2G plus 2, because this one had 2G plus 1, coming from this exact sequence. And then there's an extra one, because it's an extension to class in H1. So 2G plus 2 dimensional representation, which varies with this endpoint. So we have a family of Galois representations indexed by the variable endpoint of this association. So we've now enhanced this picture that we had before, and we've created more space on the Jacobian. And so I had to adjust a little bit the picture of Henri that I showed in the previous slide. So here's a picture of how to enhance it. I put Bas Edixhoven. This seems maybe like it's in very poor taste, but I know him quite well, and I know he would have liked this kind of playful homage. So this is Bas Edixhoven embedding instead the genus 3 curve, not in its Jacobian, but in this GM torsor over the Jacobian, so where there's much more space. So that's the idea. Okay, so finally, we have to eliminate the geometry completely by delivering a final blow and identifying a function. This is where the p-adic heights will come. We have to identify a condition on this Galois representation that is satisfied for finitely many p-adic points, including the rational points. We have to identify some kind of condition that needs to be true that replaces this Coleman integral from B to Z is equal to 0. And this condition will now not be a linear condition, it'll be a quadratic condition. So it goes through the bilinear height pairing constructed by Nekovar, which associates to these mixed extensions that we just cooked up from a rational endpoint X, a p-adic number. Yeah? And the bilinearity just means that it factors through just looking at the quotients. Just like in Catherine's talk earlier this week, you have a mixed extension. It's like, well, I'm not explaining this very well, but it doesn't matter all that much. You have an extension here of this Tate module by a QP1. And then you have a further extension of QP by this U. So it's like a matrix with 3 blocks on the diagonal, and you have these 2 extension classes coming from this extension class, and then the extension class where you forget the QP1, you just look at this other one. And then these 2 extensions are put together by a 3rd extension class, which was the lower left entry that we saw in Kathy's talk as well. So it factors through essentially forgetting this lower left entry and remembering only these 2 extensions. And that's the bilinearity of this pair. Anyway, that's kind of how it works. Now, what's important about it is that this global height pairing that Nekovar constructed entirely in terms of the Galois representation, this bilinear pairing, has a local decomposition into local factors, which are very concrete and have a more computable field. So this global height function has an expression as a sum of these local height functions where it's a p-adic height, it's valued in QP, the factor at P will be very different from the factors away from P. I say factors, or maybe I should say terms. So these HVs are all classes. They're torsors for the local Galois groups of this representation U. And they have very different flavors. And so I don't need the details in what follows. So I'll just give you an impressionist kind of a picture.
What was capital V again?
Capital V, sorry. V is the Tate module of the Jacobi.
It's the same V as before.
Exactly, it's the same V as before. Yeah. Okay, so the local contributions, they're not bilinear. They don't have this kind of factorization property. It's kind of important. But they have a very different flavor. So the contribution at P is more like an analytic contribution. So it gives you a function of the local points to QP, which is locally analytic. And it'll be some combination of iterated Coleman integrals. So it has this very kind of transcendental feel to it. The way we compute it is by computing for this Galois representation, just the filtered phi module of this thing at the prime P. And this we can do by interpolating this filtered phi modules into a vector bundle with connection on the curve, which is characterized by a couple of universal properties. And that's enough to enable us to compute it. It doesn't matter so much how we compute it, but that's kind of the flavor of this function. It's a very transcendental analytic thing. The HLs, when L is different from P, will be maps from the QL rational points to QP, and they always have finite image. In fact, they're always trivial whenever the semi-stable model of your curve at L is actually good reduction. If you have good reduction, you always get a trivial contribution. Otherwise, you have to determine what the semi-stable model is, and you have to find how many components there are, and for each component, you get a non-trivial contribution potentially. That's kind of the idea. So very different kind of things, this analytic thing, and then this kind of finitely valued thing. And so the idea is, it's kind of a silly thing, maybe the first time you see it, but there's a non-trivial condition that we can cook up on global points by saying, you see, if we find a way to find all of the possible images in this finite set, then we know that if we compute the function h, and we compute the function hp, and then we run through all of these elements in this set, this equality needs to be satisfied on the global points. And in fact, it's only satisfied for finitely many p-adic points. Set it up. So that's kind of the idea. So we find a condition, we find an equation that needs to be satisfied for global points, which is expressed by a locally analytic function, so p-adic locally analytic function. So the zeros of this function, if you bring everything to one side, contain the set of rational. It's very much like what we saw yesterday. And in fact, I mean, it's more than just a similarity somehow, I think. But okay. So that's kind of the idea. So you make this global condition by encoding all of this difficult geometry into this more algebraic object, which essentially just boils down to linear algebra in the end, because we're working with filtered phi modules, just have to manipulate them and compute all of these objects appropriately. We've eliminated the geometry in favor of these p-adic heights, which retain enough information for us to work with. Okay, so that's kind of the end of the Chabotis story. And now I want to try and echo a little bit on the RM side, things that have a vaguely similar feel to all of these constructions. Unless there's any questions before the RM side. Very good. So now we go to the RM.
I do have a question. How do you find the finitely many points such that h of x equals?
Yeah, computationally. Yeah, it's always a computational thing. So you find all of these. So this one, I mean, you solve for it by having enough rational points. It lives in a finite dimensional vector space through this bilinearity. So you solve explicitly what this is by, for instance, probing it with enough rational points. Whereas this one, it's essentially a computation of iterated Coleman integrals.
Yeah, so are these like, is this like a quadratic function?
Yes.
On
exactly. That's what this is. So the fact that this is quadratic is absolutely crucial. And so the HP is not quadratic, and that's why this thing will not be identically zero. It will only be zero at finitely many points. But so once the theory is set up and you have a way to access all of this information in all these vector bundles, then it becomes a computation. And so you feed to your computer an equation for the curve, which is ridiculous, right? I mean, the first thing anyone ever tells you about a modular curve is never write down an equation for a modular. That's the first thing you have to do when you run the algorithm. So once the theory is set up, the thing doesn't really care about the fact that it's a modular curve anymore. The method is too general in some sense. They really know a lot about non-split Cartan modular curves. The only thing it's using is that there's these endomorphisms coming from the Hecke operator. But that's a very vague, that's not a very specific thing. But it's an important thing to note is that this gives you, in these cases that I discussed, a proof that there's no other rational points, but it's also a proof where you don't really learn anything new about the rational points on a modular curve. It's just it's a proof that there's no other points, but Mazur's proof somehow maybe tells you a little bit more also, structure of the Eisenstein, etc. So all of these things are absent from this method. There's always a computation involved. Okay. All right, so now on to RM theory. And what I want to do is I want to put myself in the very modest setup of real quadratic fields, which after all the amazing things we had this week might seem like a ridiculously modest assumption, but that's kind of the setup that I want to consider today. All right, so we had these two types of invariants, the elliptic units and the singular moduli. And about the elliptic units, of course, what can I say? I mean, we've heard so much about it this week, and this week in many ways is a celebration of the work of Dasgupta and Kagde. And the elliptic units that I'll refer to, maybe the Brumer-Stark units that we've heard so much about, and I'll introduce maybe a little bit of notation that I'll use later on. For the rest, I'll let the other lectures speak for themselves. So whenever we have a totally real field, I'll take an abelian CM extension of it, and now I'll take a prime German Q that splits completely in H. This is going to be the setup that I need, and F will be real quadratic or maybe biquadratic in what follows. It'll be totally real. Okay, so now for each prime above it, so it splits completely. Yeah? So for each prime above it, there's a unique virtual unit. So there's an element in the unit group of this H that is a Q unit. So it's a unit away from Q. And it's in the minus part for complex conjugation. So this minus is very, very important. And then I tensor it up to Q. So I don't know it's an actual unit, but I do know that there's a virtual unit that generates the ideal Q over Q bar. Of course, Q over Q bar is not a principal ideal, but virtually you can always find a generator, and that's what this UQ is. So if you raise it to some power, it becomes principal, and then you take that power. Okay, so these UQs will come back later. And of course, you see, Dasgupta, Kagde, they show actually exactly, I mean, so these very specific, these Brumer-Stark combinations where you weight things by the L function or the L partial L values, give you not just a virtual unit, but an actual unit, 1 over Q star. And furthermore, they don't just prove that, they also give an explicit analytic expression for this unit. And to finish it all off, it's also computable. So you'll say, okay, what are you still going to tell us about real quadratic fields? And you would be right in many ways that if you're looking to generate extensions of real quadratic fields, I will have nothing to add. So from the point of view of Hilbert 12, this is a very convenient thing to do, especially since the singular moduli that I'll consider might also be defined over interesting extensions of F. But they have lots of prime factors. Yeah? So maybe in practice, you prefer to have small minimal polynomials that you can store on a computer and those kinds of things. So these prime factors may seem at first to be more of a curse than anything else, but as I'll argue later, they're also a source of very rich arithmetic that maybe the elliptic units don't see, and the relations between them are tremendously interesting. And that's kind of what I want to try and convince you of. So in many ways, I mean, the situation is maybe a little bit similar to CM theory also for a long time, and certainly the first part of the 20th century was believed to be sort of complete, and it would tell us everything we needed to know. And certainly from the point of view of Hilbert 12, that's completely true. You knew how to generate all of these extensions in a beautiful and elegant way. But then Gross and Zagier found that these factorizations of differences of singular moduli contained a lot of interesting arithmetic information, which gave also impetus to more geometric investigations that ultimately ended up being very relevant to the BSD conjecture. And it's a little bit in that corner that I want to put myself now and look at the prime factorizations of invariants that mimic singular moduli in the setup of real quadratic fields. Good. Okay. All right, so this is the basic setup that I want to consider. And what I'll do is, so in our first paper with Darmon, we defined these invariants that look like differences of singular moduli for real quadratic fields. And we defined them in the framework of rigid meromorphic cocycles, which have also appeared in several of the other talks. And what I want to do today is I want to give you a definition that doesn't use this language at all. So I'll just use linear algebra and give you a direct definition that fits on one slide. So it's rather short. Feels a little bit strange if you see it and unmotivated because the rigid cocycles aren't there. But it's short and concise and kind of to the point. The downside is that it's ever so slightly less general than the invariants we defined in the first paper. And I'll tell you about that in a second. They're norms to QP of the invariants we defined there. So it's up to index 2. They're the fully general story from that paper, but not quite all the way. Okay, so the basic data is I have a pair of embeddings, which I'll call alpha 1 and alpha 2, of two real quadratic orders. I'll take maximal orders in a real quadratic field, O1 and O2, inside of the maximal order in a quaternion algebra. And that quaternion algebra had better be indefinite. You can take any indefinite quaternion algebra you like, but for the purposes of today's talk, let's just take M2Q. That was the case also for our first paper. But I'll keep the notation B so you can see that it doesn't actually matter all that much. And if you want to challenge yourself, you can try and find the one or two small bits where it does matter that we're working with M2. I'll get to that. So that's the basic setup. I have my pair of embeddings. So now this endows everything with a lot of extra structure. So the biquadratic field L, spanned by K1 and K2, which are the field of fractions of O1 and O2, two real quadratic fields. That's a real biquadratic field as well. And it contains a third intermediate quadratic field, which I'll call F. Okay. Now, there's an action of this biquadratic field on the quaternion algebra B coming from these two embeddings, because L is the tensor product of K1 and K2. And if I take a pure tensor inside of there, it's enough to define the action on the pure tensors. And on the pure tensors, I just embed via alpha 1 and multiply the element on the left. And I'll embed K2 with alpha 2, and I multiply on the right. This gives me an action of this biquadratic field on B. B is a 4-dimensional Q vector space, but it's a 1-dimensional L vector space for this action. All right. Now, what's nice about this is that if I take the reduced norm pairing, determinant pairing in the case of the matrix algebra, then there's this very nice equivariance that is satisfied. So if I act on the first coordinate by L, then that's the same as acting on the second by L sigma, where sigma is the conjugation of L over F. So it's Hermitian with respect to that involution. That's what I'm saying.
L over F.
Sorry?
You wrote L over K.
That's wrong. Yeah, that should be L over F. Thank you. Okay, so now this Hermitian property implies, for silly linear algebra reasons, that in fact there's a unique way to refine the reduced norm pairing to an F-valued bilinear pairing on this quaternion algebra. And I'll denote it by the same symbol, but with a subscript F next to it. So it's an F bilinear pairing on B, viewed as a 2-dimensional F vector space, valued in F. And it's characterized by the property that if I take the element that comes out of this pairing and I trace it down to Q, I just get the usual reduced norm pairing that I had before. Okay. So this pairing depends crucially on the pair of embeddings that I took. Okay. All right, there's also an explicit formula for it, but I don't know if it's very enlightening. So it's not a super mysterious thing if it looks mysterious. Okay, now, the construction we gave is a p-adic construction. So there has to be a prime p that comes in. Everything here is still global. Now I'm going to choose a prime p, and I'm going to choose it in such a way that it's inert in both of the real quadratic fields K1 and K2. Okay. It has to be split in B. B was M2Q, so that's not really a condition, but if your B wasn't, then you have to pay attention to this. Okay, I'm also going to fix an embedding of Q bar into QP bar, and that's going to be quite important later on. But for now, it gives me a very convenient way to make this sort of one line, albeit somewhat mysterious definition. So I'm going to define a quantity which I'll call theta p star. P is because p-adic, star because it's a multiplicative condition, and it depends on this pair of embeddings alpha. And here's what it is. I'm taking a product, and it's a product that's indexed by the elements of the maximal order A, where I quotient out on the left by the norm 1 units in O1, and on the right by the norm 1 units in O2. Now, that's a huge set. That's a big infinite set of double cosets. I'm taking only the ones that are represented by elements whose usual reduced norm pairing is p to the n factorial. Yeah, so if you were matrices, then it's matrices of determinant p to the n factorial. And what I'm going to do is this product, which is still a huge infinite set, I'm going to take the factor BBF, so this F-valued pairing that we just defined, and raise it to the power sine of B, which I'll tell you in a second what that means. And then take a limit as n goes to infinity to make this thing independent of n, and lo and behold, something convergent will come out. Now, very important for the convergence is this exponent. That's maybe the most important thing in this definition.
So for a particular n, it's a finite product?
With this sign, yes. Yeah, indeed. I haven't defined this yet. If I hadn't put this sign in the exponent, it would have been horribly non-convergent, even for one n. So with the sign, everything becomes finite before the limit and convergent after the limit. And the sign is always an element of 0, 1, or -1. And it's defined to be the intersection of two geodesics in the Poincare complex upper half plane. And the two geodesics are the ones connecting the fixed points of alpha-1 and the fixed points of alpha-2 conjugated by this element B. So here's a picture. So I have alpha-1, which maybe has two fixed points, tau-1 and tau-1 prime. There's a canonical orientation on this as well. There's a stable and an unstable fixed point. So I get an oriented geodesic in the upper half plane. And for the other one, alpha-2 had fixed points tau-1 and tau-2. So this conjugate embedding will have fixed points b tau-2 and b tau-2. So what I do is I choose my favorite hand, left or right, and I stick with it. And then I compute the intersection in homology in the usual way. Okay, and fix an orientation. Okay, now this is very important, and as Samit pointed out, before you take the limit, this is actually 0 for all but finitely many terms. So you get a finite product for every fixed n, and then in the limit, it converges. Which is not super obvious, but it is true. Okay, so that's the definition. That's the definition of this invariant. And for this invariant, maybe I should say,
Should template some.
yeah, maybe I'll write this on the board. How did you know I was going to write on the board? Maybe I can use this. Is that this invariant we computed in lots and lots of examples. And we observed the following. So these were kind of the main conjectures.
You just switch so the.
Yes, sorry, that's right. Yeah. Sorry. So the people at home, I think I have to do this now. So hopefully someone will shout if you can't see the board now. We observed. So we observed two things. Two main things. And there's other things in there, but let me boil it down to the following statement. The first statement is that as soon as we pick a prime P that is 2, 3, 5, 7, or 13, then actually this quantity is an algebraic number. Moreover, it's not just an algebraic number, it's contained in the compositum of the two narrow Hilbert class fields of K1 and K2, which I denote as is tradition by H1 and H2. Contained in this compositum. By the way, just like the difference of singular moduli would be J tau1 minus J tau2 if tau1 and tau2 were two CM. So that would be contained in that extension. Here we observed the same, but we needed this condition, which looks a bit mysterious, but I hope to say a little bit about that on my last slide, explain maybe where it comes from. Okay. The second thing we observed is that these things are not just algebraic numbers, they have extremely rich prime factorization. And James Rickards did a fantastic computation of hundreds and hundreds of pages of evidence for this particular conjecture, where he showed that if you take the odd Q, where Q is now some prime inside of H1 of H2, and Q, the prime below it, is going to be inert in K1 and K2. If this condition is not satisfied, the odd Q is always 0. So these are the only relevant primes. Well, I say inert, I should say non-split. But no matter. The odd Q of this quantity, alpha-1, alpha-2, is given by a topological quantity, which is the intersection number of some pair of embeddings. Let me call it actually beta-1 and beta-2 some pair of embeddings beta-1, beta-2 of the same orders in a different quaternion algebra. So it'll be an embedding inside of the quaternion algebra where I take the quaternion algebra I started with and I change the invariants at P and Q. So if it was M2Q before, now it's the maximal order in the indefinite quaternion algebra ramified at P and Q. P being the prime with respect to which I've done the construction, Q being the prime whose ord Q I would like to know. So what that means, I mean, the picture is just that we started with our usual upper half plane, and we had maybe the geodesics coming from alpha 1 and alpha 2. And then we had the quotient, and maybe we were in M2Q, so we had a quotient by SL2Z, maybe on the left, to X of 1, and a pair of geodesics on there. Here the intersection number is always trivial because it's a curve of genus 0, but on this nearby quaternion algebra, P nearby, we get the same picture, and the prediction was that there's some distinguished pair of embeddings, beta 1 and beta 2, so that if we quotient out now by RPQ 1 star, we get the Shimura curve, which could have some higher genus, XPQ, and we're saying that there's a distinguished pair of embeddings here, so that if you look at the homological intersection of the two geodesics associated to these two embeddings, that gives you precisely this ordinance factorization. So there's a topological interpretation somehow for the ord Q of these invariants. There's a small Q weighting, which I'm shoving in the carpet, not sure that much. So it's not quite in homology. There's an arithmetic weighting that I'm not telling you about. But that was kind of the conjecture. Okay. All right. So what can we do with this? It was observed in hundreds and hundreds of examples, so there was no doubt that these conjectures were true. And these rich factorizations seemed very tantalizing, but a sort of mechanism is needed to switch between different quaternion. So I would like to tell you on the last maybe 1 or 2 slides.
What is the subscript on the int?
It's a Q, and that's because there's a Q weighting that I'm
Q weighting.
So
Okay.
it's the intersection, the homology of this, but then for any intersection that you get a pair of embeddings, and you also measure how congruent they are mod Q, and that you put as a weighting. But
Because I was just gonna make a comment, because without that, it seemed like it was symmetric with respect to P and
Yes.
Q, which is kind of funny. But with that, maybe no
that's a
longer.
great observation, and indeed that's something that jumped out at us in the data in the beginning. If you didn't put the Q weighting, it would be perfectly symmetric, and in practice also, the Q weighting usually doesn't come in, except maybe at P's 2 and 3. There's more of a tendency to get a congruence. For higher primes, it's very rare that it comes in, so you do actually get that symmetry in most of the examples. Yeah. So indeed, P and Q can be switched completely, even though they play completely asymmetric roles in the construction. That's a great observation.
This Q-adic valuation is 0 when Q is larger than the product of the discriminants over 4 or
Indeed,
something.
yes, and that actually follows from this. Yeah. That's correct.
That's my question.
So only small primes Q can appear in the factorization. So then you get very smooth numbers. Okay, so I want to tell you a little bit about this seemingly crazy definition that I have here. In this work in progress, what we do is we enhance it to an even crazier definition. An even crazier definition, but with a payoff. And so I see that I'm almost out of time. So I'm not sure if it's very useful to go through it.
Did you switch for the online?
Oh, sorry, I didn't switch. Thank you. That's in the interest of time, it feels a bit anticlimactic if I don't tell you what this crazier definition is, but then again, it's a crazy definition, so you might not enjoy it all that much anyways. So what I can do is I can give you a glimpse of the slide in the interest of. And the main takeaway from I mean, it's a little bit complicated, but it's all linear algebra essentially. It's a bit, and so it's reminiscent very much of this construction of the p-adic heights that showed up in the method of Chaboty in many different subtle ways, except there's no algebraic cycles anywhere in sight. So everything is encoded in terms of these embeddings inside of the quaternion algebras. So there's various non-integral versions, integral versions, p-integral versions, or unit versions. And what we do is we encode all this information of these embeddings inside of elements of the field F in a very specific way. And setting things up, okay, well, linear algebra. Linear algebra gives me some definition, and the definition looks a little bit like this. So all I'll do is give you a flavor. If you want to know more, ask me after the talk, but since it's already almost time, I'll just give you a flavor of what it looks like. It's a sum, it's a finite sum actually, of things that are all encoded in terms of this data of the embeddings and the base fields that we're working on. So it's a sort of an integral over the base field of a certain quantity, which is a p-adic logarithm of something that's associated to a pair of quaternion algebras endowed with embeddings. And that thing is usually just an element of the base field, but sometimes it's the norm of this UQ that I defined earlier, this virtual unit inside of this extension H1, H2. And so it's some crazy combination involving all kinds of embeddings of all different quaternion algebras encoded into one finite sum. And this finite sum I will dub the height symbol. And of course, I can make crazy definitions all day long and give them names like height symbols, but I have to follow up and tell you why that's a reasonable name for it. And the reason is the following theorem, which I want to close with. And it's a theorem that's in progress, is that this crazy definition, which involves all this kind of algebraic invariants encoded in terms of the embeddings, has actually a beautiful local decomposition. And this local decomposition reflects exactly the decomposition we saw for the p-adic heights before, where the contribution at p is the log p of this invariant that we defined in our first paper together, even though that didn't a priori appear in the definition. It rolls out of this. We get the log p of this invariant that we defined, and then we get a sum indexed by all of the primes in H1, H2, in that big extension, all of these primes of the logs of these virtual units normed down to QP, weighted by precisely the intersection numbers that we predicted in our factorization conjecture. So this kind of global algebraic definition spits out all of these different types of contributions, this being the invariant of dv1, this being some algebraic numbers. And now what do you do with this height? Here's the punchline. With this crazy definition, you can kind of see coming that there's some modular form in the background. Maybe some diagonal restriction of a Hilbert modular form is in the background. And that's precisely how this theorem is proved. There's a generating series that you can make for these height symbols, where you get alpha 1 in the first argument, and the Tn alpha 2, where Tn is the nth Hecke operator, on the second argument. And then you make a generating series Q to the n. If you make this generating series, this is actually a modular. So it's a cusp form of weight 2 and level gamma 0 of p. And it's obtained by taking the first order derivative ordinary projection of a family of Hilbert modular forms, where it's a cuspidal family of Hilbert modular forms, p-adic family of overconvergent Hilbert modular forms. That's entirely cuspidal. There's no Eisenstein series anywhere in sight. Now, this theorem, you might think, okay, what's the point of it? It kind of illuminates maybe what we observed here. Because what's special about these primes? These are exactly the primes for which this space is trivial. So this modular form is not just modular, it's also 0. So if it's 0, then all of its Fourier coefficients had better be 0. So in particular, the height pairing of alpha 1, alpha 2 is 0 in that case, in this genus 0 situation. And therefore, this is minus this. So the log of the invariant that we defined the first time around is equal to minus this weighted thing, some algebraic number with ord q's given by these intersection numbers that we saw before. Precisely as predicted in the. So when p is one of these primes, the number we get out is nice and algebraic. It's very interesting, and it has an interesting factorization. When p is not one of these primes, we don't get an algebraic number out necessarily. But maybe it's even more interesting, because now we get a non-trivial generating series for this mysterious height pairing or height type pairing.
Which field is the UQ from? Because
yeah, so so UQ lives in H1, H2. So it's a height pairing. Usually when you look at Heegner points, you trace them down to the imaginary quadratic field. We're not doing that, and that's very important. So here, so the Q is in H1, H2. So we have diagram K1, K2, Q, FL. And so here we have H1, H2.
but what is the definition? You defined UQ as the Brumer-Stark unit of like the Hilbert class field of a given totally real field. So
Well, actually, so it's this. So this is the H from before.
oh,
The
this
totally real field is going to be this L.
L. I see. So
Biquadratic field.
very nice.
So this is totally real. This is CM, and then these Q's with this condition that I just erased, they will all be totally split here. So it's exactly that UQ that we saw before. That's the field that we're working. So we're seeing that these Brumer-Star combinations give us this very beautiful kind of global unit. But here's a different kind of combination of all of the ones that involve also different primes Q, which also gives you this interesting algebraic number. So it's a different kind of topological other way of putting these virtual units together. So with that said, I think I have to first of all apologize for running over by 5 minutes, and second of all, thank you very much for.
Are there any questions?